So Paul, with the Hubble Space Telescope, we've been able to calibrate a handful of galactic Cepheids. We have the ability to observe in the infrared, but that handful of Cepheids is really going to be a problem. So for that reason, we keep on going back to our old friend, the Large Magellanic Cloud, that's got 10 billion stars, so it's got a lot of Cepheids in it. But we need to really nail its distance, and it would be good to get a distance to it which is a ruler distance, one that we know is absolutely correct, not a relative distance.
And a lot of people are working on this. There are new papers on distance to a Large Magellanic Cloud coming out every week, I'd say, at the moment. Yep. Actually, that's been the case for at least the last 50 years. Much of the early work at Mount Stromlo was working out rough distances to this. And there are a few methods now coming along which are actually very direct. And I'd like to talk about one of them because it's kind of neat and it's probably the best at the moment, though there's some competition. And this is actually a spin-off of something we've talked about in earlier parts of this course, which is gravitational microlensing surveys.
Right, so if you recall, back in 1993 at Mount Stromlo, we discovered the first microlensing of one object going in front of the others. But to find that project was looking at 50 million stars all the times. And so you get the chance to find lots of rare objects. And that project has been replaced with some major projects based around the world. And so these surveys are going through and finding very rare stellar systems in, for example, the Large Magellanic Cloud over by you, or the bulge over by me.
Yes, now if you remember we talked about this in two other parts of the previous courses. One was looking for dark matter, which was the original purpose. The idea was that every now and then something would pass in front of the Magellanic Clouds, a dark thing, and make one of the stars get brighter. It turned out that it's not a major contributor. The second thing we talked about was in the exoplanet course, when this time looking at the bulge over here, and once again, every now and then a planet will pass in front of a star at the background and make it appear brighter because of gravitational lensing. And now we're going to talk about a third use for these surveys, which is to find a particular sort of binary star. These are well-separated eclipsing binaries. Now what's going on here is you have two normal, or probably pretty big stars orbiting around their common centre of mass. It's pretty easy to find eclipsing binaries when the two binary stars are very close in, because they have eclipses very often and they don't have to be particularly edge-on before you see an eclipse. But these ones where they're much further apart are much harder to spot because they have to be almost exactly edge-on to actually see the eclipse, and eclipses are pretty rare. But these are the ones that really care about, because we want the two stars to be normal stars, as if they were isolated. In the close eclipsing binaries, the stars disturb each other. They pull matter from one to the other, they distort each other, they get tidally locked, all sorts of things are strange. Whereas these ones are so far apart that in terms of the property of the star itself, it doesn't matter that the other star is there.
And that means we can treat them as spherical cows, which means we can understand them. And if they're distorted, then all the little simple physics tricks we use aren't so easily done, and so you're not so sure about them.
So once one of these microlensing surveys has found these well-separated eclipsing binaries in the Magellanic Clouds, the first thing you do is get spectra. And you can measure the spectrum of the two different star components. You get two different sets of lines superimposed on each other, moving backwards and forwards. And what you see here is the velocity of the two stars, and one goes up and then goes down and then goes up. The other one's in reverse because they're both going in different directions around their common centre of mass.
And we can tell these two stars are very similar of mass because the two curves are almost the same magnitude in size.
It's not a perfect sine wave, which is telling us they're not in a circular orbit, but just like in that simulation, they're in an elliptical orbit. So they'll be going faster here when they're being close to each other, and they'll be going slower out here when they're further apart. But they still never get too close to each other.
Yep. So that allows us to go through and to essentially calculate what they're doing in their orbits very accurately.
So we get the speed from the Doppler effect. We can work out how many kilometers per second they're moving. So we know how fast they're going, and the Doppler effect doesn't depend on distance. So the distance doesn't matter. The second thing we can look at is the change in brightness when one goes in front of the other. Now this is a bit complicated to model because you have to allow, for example, limb darkening. The outsides of the stars not as bright as the middle, and they won't go bang in front of each other. They'll probably have a glancing incident where they clip each other. But by detailed look at this, you can work out those exact things, and by detailed fitting of this. And so from this, we know how fast they're moving, and this tells us how long it takes one to go in front of the other. So if we know speed and time, that gives us a distance. So this tells us the radius of the two stars.
Ooh.
Independent of anything.
Yeah, so you have a ruler, the radius of a star independent of the distance. And that turns out to be a very powerful tool to measure how far away these stars are, effectively figuring out how many watts they're producing.